Section: Introduction. In this section, we discuss the concept of deliberate practice, DP, as a fundamental principle of human learning. We recognize that true progress comes not from repeating what we already know, but from engaging with challenging tasks that push our abilities. For instance, when learning to play the guitar, merely practicing familiar songs does not enhance our skills. Instead, we need to focus on difficult tasks and refine our learning through feedback to make real advancements. This principle emphasizes that effective learning involves encountering informative and challenging examples rather than just repeating familiar ones. In contrast, many machine learning models are trained on fixed datasets, which limits their ability to adapt to their weaknesses. A promising alternative for visual recognition tasks is the use of large-scale pre-trained text-to-image models, which can provide an almost endless supply of synthetic training data. This raises an important question: how effective is learning when we rely solely on synthetic data? Research indicates that simply increasing the amount of synthetic data often leads to diminishing returns, where performance improvements plateau. However, removing uninformative examples has been shown to enhance training effectiveness, whether with real or synthetic data. Inspired by human learning and advancements in generative image models, we propose the deliberate practice for synthetic data generation framework. Unlike traditional methods that generate all synthetic data at once, our approach creates a dynamic interaction between a diffusion model and a learner throughout the training process. Specifically, instead of generating a complete dataset up front and then pruning it, we focus on generating data directly from a refined distribution of informative samples. By using the learner's prediction uncertainty to guide this generation, we ensure that we produce only the most challenging and informative training examples. Our framework operates dynamically. We start with an initial set of synthetic data and train the learner until its performance on a real validation set levels off. At this point, we use the learner's uncertainty to direct the diffusion model to create new challenging examples, which are then added to the training set. This cycle continues, allowing the model to consistently encounter more informative data throughout training. This method aligns with broader goals in machine learning, such as interactive learning, continual learning, and active learning. By utilizing this dynamic loop, we reduce inefficiencies from redundant data, enhancing the effectiveness of training with synthetic data. We summarize our contributions as follows. We introduce the deliberate practice for synthetic data generation framework, which adds new data points dynamically when the learner's validation accuracy plateaus. Our framework uses the learner's prediction uncertainty to generate challenging synthetic data, improving the scaling behavior of synthetic data. We provide a theoretical analysis of how a simple model trained on selected examples behaves as data size changes, showing better scaling when focusing on difficult and informative examples. We demonstrate that our method of uncertainty-guided sampling approximates generating from a refined distribution. Empirically, we validate that our approach can enhance validation accuracy compared to direct pruning while being significantly more computationally efficient. We show that our framework outperforms previous methods on both ImageNet 100 and ImageNet-1K, requiring much less data and fewer training iterations. For instance, on ImageNet 100, we generated significantly fewer samples and completed training in a fraction of the time compared to earlier work, yet achieved better performance. Similarly, on ImageNet-1K, we reduced the number of samples and training iterations while still outperforming previous results. Additionally, our approach performs well on out-of-distribution datasets, even surpassing models trained with real data on certain benchmarks. In our problem formulation, we assume that we do not have access to real labeled training data and must rely on a generative model to create training examples. We define our goal as training a classifier that maps inputs, like images, to class labels using a small validation set of real data for evaluation. Our challenge is to generate a minimal yet effective set of training data, necessitating a systematic approach to select and generate informative examples. Section Summary. In this section, we introduce the deliberate practice for synthetic data generation framework, which dynamically generates challenging synthetic training examples based on the learner's prediction entropy, improving training efficiency and performance. We also outline our problem formulation, where we aim to train a classifier using minimal synthetic data while maximizing generalization to real data, despite the absence of real training examples. Section: The need for informative examples. In this section, we discuss the importance of using informative examples in our training process. We recognize that not all synthetic samples are equally beneficial for learning. Previous research indicates that merely increasing the size of the synthetic dataset often leads to diminishing returns, as many samples can be redundant or too simple. Therefore, we should concentrate on examples that enhance learning efficiency. To achieve this, we can measure the informativeness of synthetic samples. One method involves generating a large dataset and then removing the uninformative examples. We define a pruned dataset where we select which data points to keep based on a specific criterion. The size of this subset is limited by a defined oversampling ratio. We also differentiate between the distributions of the original and pruned datasets. The pruning process acts like an important sampling method, where we use a weighting function to retain only the informative samples. However, this generate-then-prune approach can be computationally inefficient since many samples are discarded, highlighting the need for better methods to directly sample informative examples. Next, we consider approximate sampling of informative examples. We generate samples using a diffusion model, which follows a reverse stochastic differential equation, SDE. This process includes a Wiener process to model noise and a drift term that adjusts the noise level over time. Instead of sampling from the original distribution, we aim to sample directly from the pruned distribution. By applying Gersonov's theorem, we can adjust the probability measure, which modifies the score function and biases the sampling distribution. This adjustment allows us to approximate direct sampling from the pruned distribution, avoiding the need for initial uniform sampling. We also utilize denoising diffusion implicit models, DDIMs, for efficient sampling. At each step, we generate a conditional sample using a reverse update that incorporates random noise and time-dependent coefficients. We can approximate the final denoised sample and use a pre-trained denoising network to estimate the conditional score function. A classifier-free guidance coefficient helps control the strength of conditional sampling based on labels. To compute the entropy needed for our sampling, we can use the denoised sample mid-generation, allowing us to directly sample high-entropy examples by adjusting the score function. When real data is unavailable, we propose using the learner itself during training to evaluate entropy and assess the informativeness of generated samples dynamically. We introduce our deliberate practice framework for synthetic data generation, which allows us to train the learner efficiently without real data. This framework involves dynamically expanding the dataset throughout training. We start by generating an initial set of synthetic training examples using a pre-trained generative model, sampling images conditionally for each class. The classifier begins training on this dataset with a warm-up phase. Training is iterative, with a mechanism to augment the dataset whenever the classifier's performance plateaus. We alternate between training the classifier and generating new synthetic examples. At regular intervals, we evaluate the validation accuracy. If there's no improvement, we trigger new data generation. When this happens, we generate new examples from the entropy-pruned distribution, using the current classifier stage to compute entropy. The coefficient we use controls the impact of entropy guidance, allowing us to balance between regular sampling and generating higher entropy samples. After adding the new examples to the dataset, we resume training with a constant learning rate until the patience mechanism is triggered again. We draw mini batches uniformly from the updated dataset, which grows dynamically. This cycle continues until we reach a cool-down phase, where we reduce the learning rate and stop adding new data. We will illustrate the training dynamics of our classifier using this framework and validate its effectiveness in large-scale experiments in the following sections. Section Summary. In this section, we propose a deliberate practice framework for efficiently training a classifier with synthetic data, dynamically augmenting the dataset based on the classifier's performance. We utilize entropy-guided sampling to generate informative examples, ensuring that the training process adapts and improves continuously, even in the absence of real data. Section: Training on informative examples improves the scaling laws. In this section, we analyze how training on informative examples enhances scaling laws. Before sharing our empirical findings, we first explore the impact of selecting informative examples on the scaling of synthetic data. We examine a high-dimensional linear classifier trained with both uniform and selective sampling, deriving a formula for test error using random matrix theory. We consider a straightforward model for our training data, where a specific function provides the true labels, leading to a distribution over the data. We investigate how uniform sampling compares to selective sampling of informative examples in terms of generalization. We assume a set of independent and identically distributed training pairs and train a linear classifier using a loss function that includes squared loss and a regularization parameter. The selection strategy determines which examples are included based on their projection in a certain direction. We then analyze the asymptotic behavior of the test error using techniques from random matrix theory. Our analysis focuses on the spectral density of a specific matrix, allowing us to compute key moments for a test sample and derive an expression for the test error. We simplify our analysis by assuming an isotropic setup and work within a high-dimensional scaling regime where both the input dimension and sample size grow infinitely at the same rate. We find that the asymptotic test error is influenced by several key scalars, which capture the alignment between the pruning direction and the true labeling function, as well as the statistical properties of the pruning strategy. We also identify a spectral function that plays a crucial role in our theory, resembling a distorted version of the Marchenko-Pastor law. Our main result shows that the scaling behavior of test error is determined by specific scalars, with the selection strategy affecting performance through these scalars. For example, we consider a selection function that targets examples near the decision boundary, similar to using classifier entropy but simpler to analyze. Our theoretical predictions indicate that selecting hard examples improves scaling laws, reducing the number of training samples needed for equivalent performance. However, excessive pruning can harm performance. We also discuss an adaptive selection strategy, where the pruning direction is used to identify hard examples. If the pruning direction and the classifier become misaligned, what is deemed hard may not be challenging for the classifier, diminishing the effectiveness of selective sampling. Additionally, the definition of hard evolves over time, necessitating periodic updates to the pruning direction to align with the classifier's changing decision boundary. This adaptive mechanism supports the continuous data generation process we present in a later section. Section Summary. In this section, we analyze how selecting informative examples enhances the scaling laws of a high-dimensional linear classifier, demonstrating that hard example selection improves test error through random matrix theory. We also discuss the importance of adaptive selection strategies to maintain alignment between the selection criteria and the evolving decision boundary of the classifier, ensuring effective training. Section: Experiments. In this section, we describe our experiments using the LDM 1.5 model, which we found to be the best among 4 text-to-image models we evaluated. We validated our framework on 2 datasets: ImageNet 100, which includes 100 classes and 5,000 validation examples, and ImageNet-1K, where we used 50,000 validation examples. The real training sets for both datasets served as held-out test sets. We trained a vision transformer classifier with synthetic data under 2 scenarios: static data generation and deliberate practice. In our controlled setup, we trained the models for 100,000 iterations for ImageNet-1K and 50,000 for ImageNet 100. For static data generation, we generated all data before training and assessed how different dataset sizes affected accuracy. In the deliberate practice scenario, we tuned specific hyperparameters on ImageNet 100, which also worked well for ImageNet-1K. We monitored validation accuracy during training to decide when to generate new data, ensuring we didn't overfit by also checking accuracy on the full real training sets. Our findings showed that deliberate practice scales effectively with dataset size, consistently outperforming the static setup. For instance, on ImageNet 100, deliberate practice achieved the same accuracy as the static setup using only 400,000 examples instead of 3 million, meaning it needed significantly less data. Similarly, on ImageNet-1K, it outperformed the static setup with just 640,000 examples compared to 13 million. We also compared our deliberate practice approach with previous methods for synthetic data generation. Our results indicated that it required much less data and fewer training iterations while still achieving better performance on both ImageNet 100 and ImageNet-1K. Additionally, models trained with deliberate practice performed well on out-of-distribution datasets, even surpassing those trained on real data. We explored the connection between pruning and deliberate practice through two setups: oversampling followed by pruning and direct entropy-guided generation. In the first setup, we generated a large pool of samples and selected the best ones, while in the second, we focused on generating only informative samples. We found that both methods improved performance up to a certain point, after which too much selection of high-entropy samples could harm results. In terms of computational efficiency, generating images with entropy guidance took longer than standard methods, but deliberate practice proved to be much more efficient overall, providing better performance with less data. Section Summary. In this section, we validate our framework using the LDM 1.5 model on ImageNet 100 and ImageNet-1K datasets, demonstrating that our deliberate practice (DP) data generation method significantly outperforms static data generation by achieving higher validation accuracy with much less data. Additionally, we show that DP not only requires fewer training iterations but also excels in out-of-distribution generalization compared to previous synthetic data generation methods. Section: The evolution of hard examples over time. In this section, we explore how the difficulty of examples changes over time during training. We ask, does the hardness of samples change as we train? To address this, we observe the errors on examples that were misclassified when they were first introduced. As anticipated, our model gradually learns to classify these examples correctly. However, we notice an intriguing trend. The error rate for these examples was lower before they were added, indicating that the concept of hardness is not fixed. What seems challenging at one moment can become easier later, while examples that were initially simple may become harder due to changes in the model's decision boundaries. This observation points out a limitation of static pruning methods and emphasizes the need for dynamically selecting informative examples throughout training, similar to the approach used in deliberate practice. We also visualize the evolution of generated examples from the school bus category during training. Early on, these samples often display unusual colors or grayscale tones, reflecting the model's initial difficulties with color features. As training continues, we see more complex examples with unique shapes and perspectives, showing the model's growing focus on intricate features. Regarding related work, we note that synthetic data has become a vital resource for training machine learning models in various fields. For example, text-to-image diffusion models have proven effective for visual representation learning. However, the limitations of synthetic data are acknowledged, highlighting the need for more challenging and informative examples. We address the distribution gaps between synthetic and real data by suggesting that training data should match real data distributions or be conditioned on real examples. Additionally, we mention efforts to expand small datasets and the use of vision and language models to generate descriptions for dataset augmentation. Our work aligns with active learning and continual learning principles, which emphasize iterative model updates with tailored data. These methods stress the importance of selecting informative samples based on the model's current state. We also recognize the challenges associated with synthetic data, such as model collapse, where performance declines with repeated training on synthetic data. We emphasize that implementing data verification mechanisms can help mitigate these risks, and our framework enhances sample efficiency by generating informative examples through a dynamic process.